I'm going to do two examples. The first one, let's suppose a population, P of t, grows according to this differential equation. dp dt equals to 10 times 1 minus 0.1 p times p. So I have a couple questions. I want to know what is the carrying capacity. I want to know what is K, the constant, and for what value of P is the population growing most rapidly. Okay, so the first thing you need to do is to look at this differential equation you have and see what kind of differential equation it is. Okay, we know that dp dt equals to kp times 1 minus p over m, and that doesn't quite look like this, but I could really just rewrite my k and write 1 minus p over m and put the p on the back side of this. So this would mean then that my k is equal to 10, and therefore this number right here, the 0.01, isn't exactly m, it's 1 over m. K is equal to 10, and 1 over m equals to 0.1, which makes m also 10. Our maximum carrying capacity is 10. So even though you're not told that this is a logistic differential equation, you need to be able to recognize it as such by comparing it to the differential equation form that you are familiar with. And then you need to be able to identify m and k. Now our last question here, for what value of p is the population growing most rapidly? So the population growing, that's dp dt, and you want to find when dp dt is growing fastest. So when is dp dt a max? So basically you want to find the second derivative. So that's going to be d squared p dt squared. And if we take the derivative of this, let's kind of write this out as 10p times 1 minus 0.1p. We could do the product rule, so that'll be 10 times 1 minus 0.1p plus 10p times negative 0.1. So we'll have 10 minus p minus p. So 10 minus 2p, we can factor out the 2, so 5 minus p, and p equals to 5. Our critical number is 5. Now some of you guys may remember the point of inflection of these logistic growth curves. Now when you have logistic growth, they always have this S shape where the horizontal asymptote is your maximum carrying capacity, and at some point it's going to turn from concave up to concave down, and this actually always happens at half the maximum carrying capacity. Alright, well we'll continue on to a second question. Let's suppose the rate of change of a population is proportional to 30 minus p. I want us to write the diff EQ, and I also want us to solve the diff EQ, or differential equation. So suppose the rate of change of a population, so that's dp dt, the rate of change. It is proportional to 30 minus p. Now is this logistic growth? Does it look like one of the forms that we're familiar with? Does it look like dp dt equals to kp times 1 minus p over m? Okay, and I already know right now that it's not, because we should have something p minus something p squared. Only have a single p here. So that tells me this is not logistic growth. But what that means is I don't know what the solution is, so we are going to actually have to do the work and integrate. So we'll separate our variables. So dp over 30 minus p equals to k dt, and then we're going to integrate both sides. So we're going to get negative ln, the absolute value of 30 minus p, equals to kt plus c. And then I will multiply by negative 1 everywhere so that I can get rid of that negative sign. So I'll get negative kt plus c naught. I will exponentiate both sides, and that'll leave me with 30 minus p in absolute values. But I'm going to rename my constant. So I'm going to go ahead and drop the absolute values here. Notice I have a negative p that I'm solving for. I have a negative p over here, so I'm going to subtract ae to the negative kt on both sides and move the p over. My solution for the differential equation is 30 minus AE to the negative KT power. So now if I gave you an initial condition, I said that, say at P of 0, we have 10, then we could plug this in and solve for A. And if I gave you another piece of information, like at P of 2, it equals to 20, then we could also find K. And that's it.